of previous days. Okay, so otherwise, an announcement for tomorrow. We have this paper that I left you a couple of weeks ago, so we will discuss it tomorrow. And otherwise, let's continue with our topic that is about convolution. So let us have a reminder. Okay, so what is convolution? Okay, so let's say that we have a couple of signals that we want to convolve. X of n convolved with h of n. And we have two definitions for this. So one is keeping the x fixed, this one. And then it is h that is moving. The other one is the opposite. Bien, buenas noches, Diana.
Camarero, dígame, una de champiñones. Champiñones. Oh.
Okay, so in this one it is h that is moving, in this one it is x that is moving. So I'm moving in which sense? Okay, so only you know all this, but I will make it with compact signals. They don't go to infinity. And we were making that reasoning the other day, but I think it is useful to have it again. Okay, so let's say that we have an x of n that is like this. X of n that is like this. It may go to, may have whatever values here. And it may go to infinity as much as it likes. The kernel, this one is called the kernel. So this one is called the kernel, a convolution kernel. So the kernel is, I will already plot it in the m axis. Actually, because it is not moving, you can call it x of n or x of m, or it doesn't matter. So now, this one, that will be the n, the h. So it has to be also in the m axis. But now, okay, let us do it in a couple of steps. So let's make it first n. So let's say that h of n is like this. Let's make it symmetrical. And it goes, let's say, from minus n to n. Minus n, and then it goes to 0, and then to n. And now we have to calculate h of n minus m. So that means that in the m axis, now this axis is m, it is shifted to this location. This location is n. And then we have this other location, this other location. And the rest are zeros. And this point is n, sorry. And this point here is n plus n. There is also something interesting. If we distinguish the 2 points, so this is, let's say, a red point and this is a green point, then this axis is reversed. So n minus n, because of this minus here, this is the green sample, and this is the red sample. Okay, so it is reversed, and that is what the minus means. So you have to reverse, and then you shift to the location n. And then you would multiply this signal here with this signal here. You have to multiply. So I don't know how to represent that. It will be something like this. So it will be y. This is in the axis n. And then it has to be 0 everywhere except for these 3 samples that are multiplied by something different from 0. And then let's say that the first 3 samples are something like this. So they don't need to be equal. H is symmetric, but x times h doesn't need to be symmetric. And continue with the zeros. And then you have to sum, compute y of n, you have to sum all this. And so you sum everything, and then you have computed one sample of y of n. So you would have here, now this is n, and you have calculated this sample here in the middle. So this, we still don't know which one it is. This one we don't know. But this we have calculated. It is this sum. Okay, and the rest we have not calculated yet. And so this sum here, so all this sum, it goes to this sum. Okay, so the process is clear. Okay, so now this is for 1D signals. For 1D signals we know. Okay, so let us see the slides and let us follow these ideas with, the most important message here is if you want to compute the y, let us go this point. If I want to calculate y of n is equal to, n is equal 3, or n is equal whatever, what I need is a neighborhood. It's a neighborhood of y of n. So this is different from the previous operations we were doing. So to calculate a point, a pixel in the output, we were using just one pixel in the input. But now, to calculate a pixel in the output, we are using a neighborhood of that pixel. Okay, so that is different. So convolution is somehow taking the neighborhoods into account. Okay, that is what is explained here. And why it is called also a moving window transformation. Okay, so now we know, because if I want to compute instead of y of 2, I want to calculate y of 3. This y of 3, this point, will shift to the right, and then the whole window will move to the right. Okay, that is also why this is called the moving window transformation. Okay, so then let's say that we have this image, and this is a zoom of that part of the image. We pixelize, and these are the pixels. And now, what I will do is we will construct a kernel. So now kernels are in 2 dimensions, not in 1 dimension. But the idea is the same. You will take that kernel and you will compute what is the value associated to the pixel in the middle, in the output. And to compute this output, you have to take into account the neighborhood of that pixel. Okay? So the heights of those, what are the weights here? It depends on the kernel that you calculate, but that you are using. But it is a neighborhood, and it is this sum that we have been doing before. And then if you want to compute at another output, so let's say at another location, then you will shift the kernel to that location and make the same calculations, but now around that point, and the same here. Let's say that your kernel is simply an average. So equivalent in one dimension. In one dimension, our kernel would look like this. So let's make it blue. So if you want to take the average of the samples nearby, let's say that I want 5 samples around, then it will be a symmetric kernel. It has 5 samples different from 0, and all those samples, they have value 1 pi. So this is H(n), this is always label your plots. If you don't put labels, that plot is meaningless. Okay, so this kernel would take the 5 samples around the central point, compute the average, because it will be 1, so y of n would be 1/5 divided by the sum from n minus 2 to 2 of x of n minus n. So I tend to make these limits small. Okay, so n minus 2, n plus 2, x of n. This is following this definition. This is following this definition, in which x of n is fixed, and then you shift your kernel to the location n minus n, and then you have to add for the samples different from 0. But the samples different from 0, if you shift it to the location n, are those ones. Okay, so this is an average in which all the samples around, they have the same weight. Okay, so let's we will see later how to construct this in 2 dimensions. It is not difficult, it is just the same. But let's say that our kernel is that. It is one that is computing the average around a given position. So then you would calculate the average of all these pixels in these in each one of the channels, in the red, green, and blue channels. And this is the result if your kernel is of size 9 times 9. And now let's extend the idea of convolution now to 2 dimensions. So let's do it step by step. So, okay, so let's come back to the definition of the convolution that is there. And now let us write the same convolution, but now in 2 dimensions. So in 2 dimensions, it would be like this. So we have a new image. Let's call that new image J. J, let us make it first discrete. So J at a given position has to be an input image I at that location, involved with the kernel. The kernel is also an image. It's also an image. Okay, so it has to be the same. So it has to be. It has a very similar definition to that one. Only that now I will have an m that is a vector. So it will be a vector that goes from minus infinity to infinity in both directions. So it will have 2 components, x and y. And it will go from minus infinity to infinity. And it will be the same. So it will be this one, m, and then h, and r minus n. But it is the same. Let's separate this. So it has the same definition. And actually, we can also define it in that way. So here the kernel is moving, but we can also define it. You don't need to put the double sum. You don't have to specify the limits. If the limits are clear, you don't have to specify the limits. So now the image is moving, and the kernel is fixed. Okay, what about continuous images? Okay, so for continuous images, so these are for discrete images. What about continuous? Okay, so let us do it in 1D. We know better. So what is that? So the idea is to have the same kind of expressions that we have there, but now they have to be integrals instead of summations. So it will be the integral from -infinity to infinity, and then of what? We have defined here a dummy variable for the sum. Okay, so it is a variable that will not stay in the output. In the output we only have n. So we have to define a dummy variable. Which one? We will say tau. And then h of t minus tau, differential of tau, because that is the variable in which we are summing. Okay, let us do the same, but now in 2 dimensions. So in 2 dimensions, it will be the same. So the new image, J, will be, I will not, let us find. It will be the convolution of these two. Okay, what is that? So it is a double integral now, from -infinity to infinity in both. And then the input image has to stay fixed, but I have to sum in a dummy variable. Okay, so let us call it I of r prime. And then the kernel has to move. And it will be h of r minus r prime. Differential of r prime. That is the dummy variable. Okay, so those are the 2 definitions that we have there. Those are those 2 definitions. No, this is for continuous images and for discrete images. And then this kernel is also called the convolution mask or the weight matrix, and it specifies which are the weights for each one of the pixels. So here we saw it. So you have to specify which are the weights for each one of the pixels. So I was a kind of loose here, so then let us put some numbers. So let's say this is 1/2, this is 1, this is 1/2, and so on. So you have to specify which are the values for each one of the pixels. Okay, what else? Then, there is a minus sign. So the minus sign in 1 dimension means that you have to reverse with respect to this axis, okay? with respect to this point. But now we have, let us concentrate in the discrete, that is easier to plot. Okay, let us make an annotation. Okay, so this is h of 0. This one is h of 1. And this one is h of 2, h of -1. When you apply the minus sign, h of -1 goes here. Then you have h of 0. And then you have h of 1. You see? Those are the values. So they have been reversed with respect to this axis. So when you have a kernel So when you have a kernel in 2 dimensions, let's define our kernel in 2 dimensions. So let's say that our kernel is something like this. So you will have the origin somewhere. So let's say that this is the origin. So this is the 0, 0 point. So this will be h of 0, 0. And then this will be h of first x and then 1, 0. And then this is 1, 0. And then this is a 1, 1. And then this is 0 minus 1. 1 minus 1. Minus 1, 0. And then minus 1, 1. And minus 1, minus 1. Okay, those would be the values, and they take values like 1, 1/2, 1/3, whatever. Okay, but now that will be a reversion in both directions. And a reversion in both directions is what is shown here. So you have to reverse in this direction, but also in this direction. And this is what has been plotted here. So the origin stays at the same place, but then 0, 1 is reversed. And then the next one will be 0, 2. And then on the other side, we don't see because of the labeling, but it will be 0, minus 1, and so on. And what about this direction? It also have to be reversed. So 0, 1 will go here, and 0, 2 will go there. 2, 0, sorry. So 1, 0 will go there, 2, 0 will go there, and then minus 1, 0, minus 2, 0. And the same happens. The whole matrix is reversed. So now, instead of having the axis pointing in this direction, it is as if you would have the axis pointing in the opposite directions. Okay, so you have to compute the mirror with respect to this point. Okay, so I will write a few of them. So h11 will go here. h minus 1 minus 1 will go there. But now, this is the end plane, the arc plane, in that notation. This is the arc plane. This is the M plane. And this signal here was h of r. This image here is h of r minus m. And we are plotting in the M plane. Okay. So that is an inversion in the same way that there is an inversion in 1 dimension. There is an inversion of your kernel. Okay, this is. And now, once you have inverted your kernel, you have to move your kernel, your inverted kernel, to the location you want to compute, and then multiply each one of these neighborhoods by, or each one of these points in the neighborhood by the values in the kernel, and then you sum everything, and that is the value that will go to the output. Okay, so this is the output, this is the input image, this is the kernel, and you have to multiply each point in the input image by the kernel. You will have a lot of values, you have to sum them, and then you substitute. Clear? Okay, then. Yeah, so this is an example of one result. So you have the original, and this would be the output if you take an average, a kernel that is. Now we can figure out what is an averaging kernel. So an averaging kernel would be something like this. So it would be a kernel. There's 3 times 3 that has 1/3 sorry, 19 in all locations. So it is the average, because you are adding 9 numbers, you have to divide by 9. Okay, so this is the kernel that has been used to compute that 3 times 3 average. Okay, and that region is used to calculate that point, and then this region, you may see that it is shifted. So that region is used to calculate that point, and then you shift. That is why it is called a moving average or a moving window transformation. Okay, so let us see this process. See this process now in my computer. So let's stop sharing here. So let us stop sharing. I will stop sharing my computer. We have to go here to this window. Okay, a little bit bigger. Let us see that process. So we have here the convolution, spatial convolution. So let's say that we have this image, okay, any numbers there. We have this kernel, whatever that is. Okay, so it has the central pixel, and then it has minus everywhere, and the central is multiplied by 8. And then we have to multiply. We want to compute this pixel here. So to compute that pixel, I have to take that kernel, move it. I have to reflect it, but because it is symmetric, I don't see the reflection. Okay, so I don't see the mirroring. But I have to multiply this value by this value, this -1 by this value, and so on. And then after the multiplication, this is what I get. And then I have to sum all those values. And then the sum is 74, and that will be the output. And then I go to the next one. And then you go to the next one. You multiply all these input values by these input values. And then you sum, and then you will have the output. And you keep moving your window and multiplying, and then making your calculations. Okay, so you calculate them all. Okay, then what happens with these borders? When you try to calculate a pixel in the border, the value is ill-defined, because you move the kernel. Let's move it 1 position more to the right, and then these 3 samples, these are blue, green, and blue, they are out of the image. So what do you do with them? Do you multiply by 0? Do you multiply by, but these values, they don't have 0 values, so multiplying by 0 would be kind of strange. So one possibility would be, okay, so if you need samples from the right and you don't have them, so you may replicate your image. So you may copy your image, once again to the right, and then you would be multiplying by something that is more or less meaningful. And this is this periodization that we did already for the Fourier transform. You remember that for the Fourier transform we did the same trick. We took an image and we replicated it many times. So this replication is the same. Actually, you know that the convolution can be expressed, so the convolution of 2 signals is the multiplication of the 2 Fourier transforms. That is true if you do the replication. If you don't do the replication, that is not true anymore. So if you want to implement the convolution as a Fourier transform or as a multiplication in the Fourier domain, you have to replicate your images. Okay? And if you don't do, then the borders are Okay, it is up to you how you implement the calculations on the borders. There are several sensible ways. So replication is one that substituting by zeros, depending on the context, it may also make sense. Just for you to be aware that these, whatever you do, has implications, and you need to be need to know those implications. And then you may change your kernel. So this is called the Laplacian kernel. This is called the sharpening kernel. This is called the vertical derivative. And you see it is 1 to 1, 0, 0, 0, minus 1 to minus 1. So we have multiple. This is a smoothing kernel, so this is a weighted average. Okay, so now we understand convolution. Okay, so let's move to, let us share the screen again. Okay, then. Okay, so let us see a property. So there is a property convolutions that I know. That is, if I convolve y1 is a delta, let's say, convolve with h, right? This is h shifted to the location of this delta. So if you have a delta, at some point, so let's say, let's put some figures, some ideas, please. So let's say that we have a delta that is shifted by 1. This is your x of n. That has this expression with n0 equal to 1. And now you have your kernel that is like this. This is h of n. The convolution of these two should be the kernel shifted to the location of the delta. It has to shift by 1. And this should be y. So if you convolve anything with a delta, that thing will move to the location of the delta. Okay, so let's see if that is true also for images. It will be. Okay, so let's see how. Okay, so let's say that we are convolving this delta with this kernel. The result should be the kernel shifted to the location of the delta. And in the kernel, you have to define the origin. We did it here. We did it here. So every time you have a kernel, you have to define the origin. Sometimes you don't specify the origin, assuming that the origin is in the middle. Okay? But if you don't say anything, the origin is in the middle. But otherwise, you have to specify. So we are specifying the origin here by this dot. So this dot should move to the location of the delta. And that is what should happen. Okay, so let's see how we get that result. Okay, so let us follow the definition of the convolution. So the definition of the convolution, I have to mirror my kernel. So this will be the mirror kernel. You see that here I have an L, I have here an inverted L. Okay, so, and I have to move my inverted kernel everywhere and then multiply by the underlying image and sum all those values. And here we are only representing those locations where the multiplication is different from 0. Let's say that you move it to here. So you move it to here. The underlying signal has zeros everywhere, so it doesn't. You don't care. You don't have to multiply the kernel by all the zeros and then sum. Okay, so it will be 0. So which are the locations with values different from 0? This will be one location. This one here. So this one here my inverted L multiplied by the delta will have a point that is different from 0, that is this one that is highlighted. So it will be 1, okay, because the kernel has value 1, then y is 0 here in this representation. So y is 0, the delta is 1, and the rest is 0. So I have here 1 by 1 times 1, that is 1. And then at this location, I will substitute by 1. So I have constructed this point here. You see? This will give me this blue point. Okay, now I have a blue point there. Okay, let's look for another location that the multiplication is different from 0. This will be one of those locations. So now this gray point is 1 times 1 again, and the sum, and all the rest will be 0. And then the sum will be 1 again, and I have calculated this new blue point. And then this one is also different from 0, this one is also different from 0. And all the rest, here we have 1, all the rest are zeros. Okay, so the only 4 locations that are different from 0 are this one, this, so this, and that. And then all those sums are 1. And if you collect all those blue points, this is what you get. You have the L. So it behaves as it should. So delta convolved with the kernel shifts the kernel to the location of the delta. And in the middle, in the process, I have used the middle kernel. I have to use the middle kernel. Okay, so this is many kernels that are used in image processing. Many of them are symmetric, not all of them, but many of them are symmetric. Because there, in principle, there shouldn't be any preferential direction. So x and y should behave similarly, and then that is why they're symmetric. And symmetric means that this is the center value, and then these 4 values are the same, and then these corners of the square, they're also the same, and so on. So if this is the origin, if you take the mirror of any one of the points, you get the same value. So what is the mirror of this? The mirror of this is this one, and they are both B. The mirror of this one is this one. The mirror of this one is this one. The mirror of this one is this one. The mirror values, they should have the same. And this is a property that we already know how to express mathematically. So mathematically, it must be that h of r is equal to h of minus r. When a signal fulfills that property, how do you call it? Even. You say that that signal is even. Okay. It is the opposite of odd. So odd signals are those for which you have that they're the same, but with different sign. So these are even signals, these are odd signals, and you might have signals that are not even nor odd. Okay. Okay. And this mirroring is equivalent to a rotation of 180 degrees. So if you rotate, better seen I think here. If you take this image, you rotate it 180 degrees, and you get this one. This is the same as mirroring in both directions, but in the case of 2 dimensions, it is simply mirroring. Rotating. In more dimensions, it is not. But in 2 dimensions, it is simply rotating. Okay. And here. So there are three ways of computing the convolution. So two of them we have already introduced, that are this moving window transform and this shift multiply add. And we will explore this one a bit further. And then the Fourier transform. And then the Fourier transform is, we already introduced the Fourier transform last day, and then we will see it later a bit more. Next lecture is about convolutions in the Fourier domain. Okay, so moving window transform. So let's go to the definition of the convolution. So we have it here. So we have two ways of computing the convolution. This one here, this one is what is called the moving window transformation. And we understand that why it is called like that, because the kernel is moving, and we just understood how it is working. Okay, what about this one? This one, the one that is working, that is moving, is I. So it is the input image. So this is called the shift multiply add. Okay, so let's see it in one dimension, because I think it is easier to understand. Okay, so let's move it to this example. So let's think of this example here, and then let's say, okay, I want to compute y of n. Y of n is x of n convolve. Let me be loose about the notation. I think it is interesting to do that. So I have to convolve with this, and all the rest are zeros. All the rest are zeros. So this is my kernel. I want to convolve with that. Okay, now let's not be loose about the notation. So that thing I can write as x of n convolve with what? Okay, so then convolve with 1/2 delta n plus 1 plus 1 times delta n plus 1/2 delta n minus 1. You see? And because the convolution is a linear operator, this will be the same as x of n convolve with 1/2 delta n plus 1 plus x of n convolve with, I will not write the 1, delta n plus x of n convolve with 1/2 delta n minus 1. But now I know what this means. So let us convolve an easy signal, because this one, this one is too complicated to draw. So let us say that x of n looks like this. So let us make x of n like this. But this is easy to draw. This is x of n. This is n. Okay, so now, and let's say this is 1, this is -1, -1, just to make easy numbers. Okay, so then, what is this signal? So this is equal to, let us make it red, because we are convolving with the first one. So again, that will be loose. Okay, so this will be, I have to multiply by 1/2 and shift to the left, because anything convolved with the delta is that something shifted to the location of the delta. So this will be like this. And then we have to put heights, okay? But it is 1/2, so this will be 1/2. Okay, good. Then, what about the second? The second, I have to shift to the central location. And I have to multiply by 1. So this will be the same. But now this is 1 minus 1. And then I have to do the same with the third one. So I have to do the same with the third one. So do it like this. And this is again minus 1/2, 1. So now we start getting the name. So what is the name again? Shift, multiply, add. So we are shifting. So we are shifting to the right location, multiplying by the appropriate coefficient, and then we have to add. Okay, let's add. So what is addition? Okay, so let us look at this sample here. So for the first sample, that is all the rest are zeros. So I will get -1/2. Okay, and this is at location. Let us put numbers. So this is location 0. This is 0. This is 1. This is 0. This is 1. This is 2. Okay, so at location 2. What about location 1? So at location 1, here I don't have anything. Here I have -1 plus 1/2. So it will be again -1/2. What about 0? So 0 I have -1/2, -1/2, and then 1. So this will be 0. And you keep doing the same. This is -1, and this is -2, and this is 0. So if you convolve this signal with this one, this is what you get. And now you understand the process. So it is shift the signal, multiply by the appropriate coefficient, and then add all of those copies to have your output. So probably it's time to break a break. Okay, so let's continue. There is an interesting comment here. Okay, so let's think of this process. Okay, so let's do it with images. We are more used to have values. Okay, so let's say that this one here has 8 bits. We represent our gray images or our channels with 8 bits. And this one also has 8 bits. In general, the convolution, how many bits do I need to store it? 8 bits or something different? In general, you will need 16 bits. So all those multiplications, they can go up to 16 bits. So they may go up to numbers that need 16 bits to be represented. So in general, they go up to 16 weeks. And then you may use some quantization here, some quantization of the intermediate result to come back again to 8 fields. So now, after the quantization, get back to 8 fields. But if the intermediate results, you need a higher precision. Okay, good. Then, okay, so let's see this second process. Okay, so now we understand how it is done in one dimension. So let's see how it is done in images. So, yeah, let's see that property we already know now. But in general, it was here. Okay, so in general, let's be a bit more general. So if you have a coefficient in front A, then that coefficient is K. Okay, so if you have A delta time convolved with something, what you will have at the end will be this something multiplied by delta and shifted to the location of the delta. And that is actually what we were doing here. So in this example, we were doing exactly that. Okay? So we were convolving something with the coefficients times a delta. And then we were shifting that something to the right location and multiplying by the coefficient. Okay, so that is what is expressed there. Okay, so here you have an image convolved with a weight times a delta that is shifted to some location. This location is rho chi. So what you have, the result of this convolution will be the input image multiplied by the weight, and then the image is shifted to the rho chi location. Okay, then let's have a few examples. So let's say that we have this image, we are convolving with this kernel that has one there at the location minus the location 1616, and the origin of the kernel is there, but it has a 0 value there. The only one is that one. Okay, so the convolution of these two should be the same image with the same height because the weight is 1, and then shifted to the 1616 location, and then it has to be shifted down by 16 pixels in each direction. And that is what we have. And then if you look at the borders, you see that this border now is smaller, okay, because of the shift. Okay, so now let's say that we have two copies. So one is at 1616, but now it has only weight 1/2, and the other half of the weight is at the 0,0 location. Now we have two copies. One that is shifting down, the other one that is stays fixed, and then we are computing the average of the two. Okay, the average because the weight is 1/2. And then we see the effect of this shift. You see that everywhere you see the shift. And for instance, now this is a model to a shaking camera. So let's say that you are taking a picture, you are shaking your camera while taking the picture. You would get this. So now you know how to model that. So you know that your shaking camera looks like convolving with a kernel that has different weights at different locations, at different spatial locations. Okay. Now let's say 1/3, 1/3, 1/3. We see here the shaking flower. Yeah, nice thing. Why don't we see the shaking in this one? Because it is aligned with this direction. So this direction is orthogonal to this one. Okay, but this flower is aligned with this direction, and then the shaking occurs along this direction. We don't see the shaking as well as in that other flower. And then you can have all kind of combinations. And even, for instance, let's say this is a kind of exaggerated example in which the sheets are 16 pixels in each direction. But you may have a much smaller shaking. So instead of 16 pixels, you may have it of 1 pixel. And then it is simply a blurring kernel. But even if we don't see so much of a difference between these two images, we know that this should be a little bit sharper than this one. So we are taking averages of local values. And here you see why of this effect. Okay, so here you see this very small detail that is much more blurred in this other image in the output. And there is something interesting, that is, once you know, it is not explained there in the slides, but once you know how to simulate something, because simulating blurring doesn't seem to be very useful, right? So you want images to be sharp, not to be blurred. Depends for what, but in general, you want them to be sharp. So, but if you know how to simulate these, so let's say that, and here comes the image formation model. So let's say that you say, okay, my observed image, I will drop the arguments. So my observed image is an ideal image times or convolved with a kernel. And you know how the kernel looks like. So you know how to model the kernel. So that would mean that if you are given the ideal image, you would know how to blur it to get the kind of images that you are observing. Okay. And if you know that, then you can solve for your ideal image. So let's do it in this way. You do the Fourier transform. Fourier transform for us was always great. So you do the Fourier transform of the observed image. You do the Fourier transform of the idea that you don't know, but you know it has a Fourier transform. And then this Fourier transform has to be multiplied by the Fourier transform of your kernel. So you know this one, you know the kernel. So you know the observation, you know the kernel, but you don't know, you don't know the ideal image. But now you can solve it. So you can say the ideal image, the Fourier transform of my ideal image has to be the Fourier transform of my observation divided by the Fourier transform of my kernel. And this will be an estimate of what is the ideal image. So now, if you know how to blur something, automatically you know how to unblur something. So this is blurring. This is blurring. This is unblurring. Actually, if you do the inverse Fourier transform of this. So I can express this as this one multiplied by 1 over h. So this is a new kernel. This is a new kernel. And I will call h minus 1. So if you know how to blur something, there exists a kernel such that the ideal image is the observed one convolved with inverse Fourier transform of this one. So if you know how to blur, you know how to unblur. So now this is unblurring. So simulation is extremely important, because if you know how to simulate the process, automatically you will find ways of reversing that process and doing the opposite. And if you know, okay, I have a shaking camera and I am able to estimate the shaking, now I can recover my original image. Actually, your phones are continuously doing that. There is no way that when you take a picture, there is no shaking. You always have a lot of shaking. But there is some software that is correcting the shaking, the shake movie, or the shake picture, to recover the ideal one. It is named this convolution. So if you know how to simulate something, automatically you know how to invert that process. Sometimes the inversion is not easy, but so simulating is really, really important. And this is our image formation model. You may remember from the first day when we had the light and the sun there illuminating whatever. So this is our image formation model. It is extremely important that you understand how your images are formed. If you know how they are formed, you can recover any part of that equation where you like. Okay, then, yeah, this is a convolution with our with our kernel with 5 deltas. And this is this process that I have explained with 1D signals, but now with 2D signals. Okay, so let's say I have an image, that is the blue one. Sorry, the red one. So I have this red image. And I have to, I want to convolve it with this kernel. So now, convolving, this is a kernel that is made of a sum of deltas, and this is the weight of the first delta, the weight of the second delta, the weight of the third delta, and so on. So all I have to do is to shift the red image to the location given by that delta, multiply by the weight, and keep all those images. So I will shift the red to the location of each delta, so it is one pixel left, one pixel up, then multiply by this weight, and I will get a new image, that is this red one. And then I will shift up and multiply by h minus 1, 0. And then I will get this one, and this one, and this one. So all these red images are the equivalent of this image, of these 1D signals that I was drawing here. So they will be the equivalent of all those. And I have to add them all. So now I have a lot of copies of those images, so I have to add them. And this blue image here, this blue area, is the maximum extension that my sun can take. And this was also seen in 1 dimension. So in 1 dimension, my signal went from -1 to 1 in n, but my output goes from -2 to 2. So the output of a convolution is always wider than the original image. It is wider because I have to shift it to multiple locations and multiply by something and add them all. So the output has to be wider than the input. So this is what we are showing here. So the red, the output that is blue, will be wider than the input. And I don't think we have exact equations for how much wider, but we don't get how much wider. Okay, so now let's see if this convolving with the delta behaves the same. Okay, so let's convolve this delta image with this kernel. So this kernel tells me, okay, you have to shift it left and up and multiply by 1. Okay, so I shift left than up, multiplied by 1, so we have a delta there. Now you have to shift it up and multiply by 0, so you will have full of zeros. You have to shift it up and right and multiply by 0. Then you follow the instructions given by the kernel. Then you have a delta. You only have a delta here, 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 and there. Okay? You add all these 9 images, and you get the delta back. So this behaves as expected. So if I have something combined with the delta, I should get that something, no matter how I do it, whether with this shift, multiply, add, or following this other procedure. The kernel is reverted and then moved along the image. Okay. So, yeah. This is the same. This is simply an explanation of the process. Okay, now how much bigger? So as I said, we don't really care much. But let's try to be precise, but don't pay too much attention. Okay, so now let's say that we have an image that is of size m times n. We don't, yeah, r times c. Okay, and our kernel is of size n times n. Then, how much bigger is the output? Okay, so the output, you need extra space on the left and right that are given by this n divided by 2, n divided by 2. And you need to assume, so this is true if the origin is at the middle. If the origin is somewhere else, then these calculations are a bit different. But the idea is the same. So the output will be a little bit bigger. How much bigger? Approximately half the size of the kernel on each side. Yeah, so this is the same idea, but now shown differently. Okay, this shift multiply add. Okay, so this is a nice representation, I would say. So let's say that we have an input image, that is this one here. And then I want to convolve with this kernel. The origin of the kernel is at the yellow point. So I will multiply, I have to shift the input image by 3 pixels. So all these are zeros except the color pixels. So I have to shift my input image by 3 pixels left and up and multiply by the blue coefficient. Blue coefficient is 1/2, whatever value that is. Okay, and I will represent it like this with blue. And you see it is shifted 3 pixels to the left, 3 pixels up. Okay, then you have to multiply by this other pixel that is shifted to left to up, and then you have this other copy. And then by this one, by this one, by this one, by this one. And then you have the multiple copies that are shifted following the pattern of the kernel. And then you have to add all those values. So it is convenient for this convolution to have a kind of accumulator. So you shift by this amount, multiply it, and you keep it in some bigger image that will add as an accumulator. And then multiply by this one, and you add on top of whatever you have already. And then you multiply by this, and you add on top. And you multiply by this, and you add on top. So how many images, how much space do we need in memory? We only need 2 images. So one is the input, that we need to keep for doing the applications. The other one is the accumulator. That's it. We don't need anything else. We don't need to keep in memory all the extra copies. We only need to accumulate them. And the accumulator is related to this sum. So you make the first shift and copy, and then you keep the addition. And now when you are doing the second, for the second, you don't need an extra space. It is nice to draw, but not for computing. So for computing, you may do the calculations. So first one you do this, then you do this, and then finally do all that. So this is the sum. This is the sum. And then this accumulator has the partial sum up to that point. This is then again the same. So something interesting that is, okay, so if we look at the blue image, okay, so let's put it differently. My input image had size RC. Okay, my input image has R rows and C columns. But my output is bigger. That is inconvenient to, it is inconvenient to have bigger images or every time that I convol. So let's try to keep the central part. And the central part is again of the same size as the input. It is located at the 0, 0. So it has the same location as the 0, 0 point of your kernel, okay? The yellow image in this example. And actually, that is what the Fourier transform is doing. When you implement the convolution with the Fourier transform, what you are doing is simply keeping this part. Okay? So the Fourier transform cannot give you all this extra value. Cannot. And this is also important to know. Actually, this extra value, because the Fourier transform is making this replication, it is as if you take the accumulator image and you replicate, but with the periodicity of the input image that is smaller. So all this extra padding space is getting is clashing with the borders of your input image. So the borders of a convolution implemented with the Fourier transform are so and not so good because of this clashing. Okay, so let's see another use of the convolution. So we can use convolutions, and you saw it in this example that I showed you before in my computer. So one of the examples was vertical derivatives. Okay, so let's see how I can compute vertical derivatives with convolutions. Okay, so let's say that I have a couple of images, this one and this one. So this is artificial, this is natural. Now, what doesn't? Okay, it moved, but I didn't see. Okay, so we have original. Now we convolve with that kernel. That kernel is a 3 times 3 blurring kernel. And we already know this kernel. And okay, a few of the borders are a bit more black, as it should. So let's look at those borders. They are black now. And the reason of the blurring is that when the kernel is, let's make it the other one. When the kernel is in the middle of a square, all the values are the same, and then the average will be the same as all the values in the square. But when the kernel is touching the border, half of the values will be black, half of the values will be white, and then the average will be gray. And that is what's happening. There is a transition from black to white that goes through gray. And the same is happening here, but now here we don't see so much. You see, a little bit sharper than original one, but not so much. And the more you blur, the more, the less sharp that the output image is, as expected. Okay, and you can blur a lot. Okay, now let's look at this. Okay, can I design a kernel such that when I see this image, that is, let's say, 0, 1, and 0. When I see that, can I detect the borders of where the one, this is a step function, so where the borders of that step function is. And for that, I will design this kernel. So let us look at the kernel. Okay, so let's move here. Okay, so let me design this kernel. The central point is there, that is the 0, 0 point. It will have 1 and then -1. And all the rest will be 0. Then, how can I express this? This is delta xy minus delta x minus 1. Remember, this is the x-axis, this is the y-axis. The origin is there, but I have made the drawing of the axis there, just for not make it to this difficult complex. Okay, so sorry, I'm missing the y. Okay, now let's compose any image with that. Okay, so let us compose J of x, y is equal to y of x, y or with that thing of delta x, y minus delta x minus 1. Okay, then what is that? It has two terms. So the first term is I convolve with delta. But this delta is not shifted and it has weight 1. So it will be simply the limit. Now I have I convolve with that. And that is I x minus 1 y. So let's make brackets. Brackets are for discrete signals, parentheses for continuous signals. Okay, so that means you take a pixel and then you take the pixel on the left and you subtract. You see? Okay. So you take a pixel, that is this expression. That expression is exactly the same. Okay, so you take a pixel, you take the pixel on the left, and you subtract. That is your output. So all this time would be 0 minus 0, 0 minus 0, 0 minus 0. When you reach the border, you have 1 minus 0, so you will have a 1. And then in the middle of the pass, you will have 1 minus 1, that is 0 again. 1 minus 1, 1 minus 1. So you have a lot of zeros until you reach the border. At the border, you have 0 minus 1, that is minus 1. That is why this one is darker than this one. Okay, so the values are 0, 1, 0, minus 1, and 0. So now, by convolving with this kernel here is capable of identifying vertical borders. Okay, so this one can detect vertical borders. And it is related to something. Okay, so this one is called backward difference. So backward because you are taking one pixel and you're computing the difference with the previous pixel. So that is the difference with backward. But I could have designed my kernel like this. So this kernel is called, let's make it backward difference. But I could have designed my kernel in this way. This way. So always specify what is the origin. This is the origin. I could have designed my kernel like this. And now I am subtracting not the pixel on the left. This is the pixel on the left. Remember that we have to turn this 180 degrees. But I'm subtracting the pixel on the right. So this is forward difference. Forward difference. So now, instead of having 0, then 1, and then minus 1, I will have minus 1 and then 1. And my borders, they are actually, it depends on how you define your border. So what is your border? It is the first pixel inside the pulse. If it is the first pixel inside the pulse, this one is fine. But this one is 1 pixel off. You see, it is 1 pixel outside the pulse. What about this one? Now the right pixel is correct, but the left border, so the right border is correct, but the left border is 1 pixel off. And why not having both? Why not designing a kernel that is the addition of the two? So I take this kernel, add them, and then I construct a new kernel. And this new kernel will have 2 minus 1 minus 1 0 0 0. And now I always have the same structure for the borders. So I have a 1 inside the pulse, a minus 1 outside the pulse, and I have an edge detector, a vertical edge detector that responds similarly. It doesn't matter if we go from low to high or high to low. Okay, why these things are called derivatives? Let's think of the derivative of the signal. Okay, so let's make this. You have a signal, let's say, you have x of t, this is t. And I want to compute the derivative at some point. I want to compute what is that slope. Okay, so you know the definition. So x prime at t is the limit when h goes to 0 of, let me do it this way, x of t minus x of t minus h divided by h. Now, you know that was the derivative coming from the left. Okay, so let's see what it means. So this part here, so this part here is a point that is separating, this is t minus h. We are taking this sample, we are taking that sample. So let's use different colors. So this one is this one. And then you are dividing by this separation, this h. So this is the derivative from the left. What about the derivative from the right? the derivative from the right will be defined like this. And then x of t minus x of t plus h divided by h. I will keep this the same color, but this one will now be red. Okay, so the derivative from the right, what I'm doing is taking another sample. Now from the right, the separation is also h. The separation is also h. Okay, and if the function is can be differentiated, these two derivatives should be the same. So the derivative from the left and the derivative from the right should be the same. Okay, now let's think. Let's think of this signal, the same signal, but now I will take samples of it. I'm taking samples, and the sampling step is h. What is this? This is x of n. Let's make it green. Let's make it green. So this is x of n. This one on the left is x of n minus 1. And this one on the right is x of n plus 1. So the derivative takes the limit when h goes to 0. I cannot go to 0. But approximately, this is equal to x of n minus x of n minus 1 divided by h. And this is approximately equal to x of n minus x of n plus 1 divided by h. And this is my curve. These are the convolutions with my curve. You see? You have the same kind of expression. So this kind of operations, these forward differences, backward differences, they are related to derivatives. So it is as if you are calculating the derivative. The only thing that is missing is this dividing by h, but dividing by h is a constant, so it is a scaling. So you don't mind so much about scaling up or down. Okay, so these backward and forward differences, they are ways to compute derivatives. Okay, good. Then, what if I have a square image and I construct this kernel? So now I know that I have a vertical edge detector. What if I use this kernel? If I use that kernel, what I have is an horizontal edge detector. So, or dependent. So if you are coming from here, the edge is vertical. If you are coming from there, the edge is horizontal. So I have an horizontal edge detector. What if I want to have a detector in both directions? You simply have to add both kernels. Now you have a detector of edges in both directions. And this is related to our visual system. You may remember, we only see edges. There are cells that are, or combinations of cells, that are responding in this way. There are combinations of cells that are responding in this way. And then our brain somehow is adding everything, combining everything into a single image. But the low-level part of our visual system behaves in that way. Okay, so now I can take those two images again, compute the vertical differences. Okay, so now I am detecting only edges in this direction. Let's look at the image again. I had a pattern, so these groups of cells, they are blind to this part of the image. They're blind because there is no derivative in there. All these derivatives are 0. There are some little jumps here because of the contrast. So those jumps are translated here. So, those jumps here, they are translated into these small dots. But otherwise, in the rest of the area, I'm blind. I cannot see those because they are aligned with my kernel. My kernel is not computing any derivative there. And the same happens in all these squares. So all these squares in this direction, all I see, so in this direction, I don't see anything in this middle points. So I need some other group of cells to see those. And the same happens with natural images. Now there will be another group of cells that are computing derivatives in other directions. Actually, we don't have only two directions. We have many directions, and then we combine them all. But the same happens if I compute derivatives in this direction. I'm blind to these edges. So look at that. So there is no derivative along this direction. And I can have both. So let's use one direction. So I can add both of them, and now I see all the edges. And I can even compute diagonal differences. So why not making my derivation along this direction? I can compute the derivative along that direction. Or the opposite direction. And then it is funny, for instance, here, we understand now why. So the house, the roof, in this direction has two prominent directions, this one and this one. Okay, so the derivatives, when I compute the derivative along those directions, so for instance, this one, my derivative is here, so I'm blind to this edge. And now, the derivative is there, so I'm blind to this edge. And the same here. So the derivative is in this direction, so I'm blind to this roof, this side of the roof. And then you can add them all. And you may remember that this was the Laplacian kernel that we had. Do you remember this Laplacian kernel? That was one of the examples. They were this -1, -1, 8 in the middle, and then -1 everywhere. But it was not kind of magic. Why those numbers? Because they are coming from derivatives. So this is the addition of horizontal detector plus vertical detector plus two diagonal detectors. I think we have those here in my example. So let me check. I think we do. Okay, so yeah. So I have to stop sharing. I will stop sharing here. Start sharing in mine. Here we are. And let's say I have this image. I construct and I have many possible possible kernels. So let's say I make this one. Why is it not working? Okay, so now it will. Here, convolution. Edge. I think it's better this one. So now I have this original image and this kernel. And you see that the kernel is giving more weight to the central pixel and then less weight to the surroundings. So it is a kind of weighted average. We can make it bigger and bigger. So for instance, for comparison purposes, this one is smoother than this one. You have lost all the details in the actual network. But if your microscope is giving you this, and you know what the kernel is, you can invert the process, and you can recover this one, or an approximation of that one. Okay, what else? We can have edges. Now we understand this edge. So those are derivatives in the vertical direction. So I have derivatives in this direction. I have all the horizontal borders. And I can have the vertical borders now. You see, these borders are vertical, horizontal, these borders are vertical. And I can have both. I have both that are these Laplacians. I will have this one. The contrast is not great. So you can, for instance, this one, now you understand it. This is again, this embossed filter is a kind of derivative. You see, -1, 1, so it is a kind of derivative. Embossed heavy. Now it is a kind of derivative, but you are taking advantage of the nearby pixels. So now you understand a lot of looking at the kernel. You understand, okay, what will be the properties of the output. So this has to be a derivative, an edge detector in this direction. So, any question? No? Okay, so for tomorrow we will discuss this paper. Try to prepare it